What's going on, everybody? Welcome back to another video on Lemon's Math. This video will be the beginning of a new series covering a new topic in the differential equation page, and as you can tell by the screen, we are going to be discussing about partial differential equations. And so y'all might be getting mixed feelings about these. Y'all might be excited, y'all might be dreaded, y'all might feel, ugh, this. I don't like the sound of this. I've heard terrible things about it. Well, they over-exaggerate, in my opinion. When I took this course, it was probably like the best course I've ever took. It was really fun. It was, I'll admit, difficult, but in a very fun way. And so what this video will be covering will be like kind of the general information of partial differential equations before we start getting into the nitty-gritty of actually solving these. And so we are going to start off with the question of the day, which is, what is a partial differential equation? And so, to be honest, when you think of a partial differential equation, you think like, what is it, part of a differential equation? That was my first thought when I heard about partial differential equation and partial derivatives, but it is actually not the case. It is not part of a differential equation. It's not part of an ODE either. It's its own separate thing. It's kind of ironic because you'll think of a partial differential equation sounds something much more simpler than an ordinary, but it's quite opposite. So a PDE is, well, a partial differential equation, we also, it is also known as a PDE, is a differential equation that has more than one independent variable. And so some examples can be time and space, space and space itself. So the XY plane, they can be independent from each other. And the way the equation looks is in somewhat similar to what an ODE is. The only difference is that we are going to be using the lowercase delta. And that is to signify the fact that we are taking the partial derivative of a multivariable function with respect to a specific variable. One of the useful things about PDEs is that they can help us solve boundary value initial value problems. And this is what majority of the series is going to be about, solving these types of problems. And so what makes up a boundary value initial value problem? Well, three things must be known or given in order to solve such problem. And so the first one is the partial differential equation itself. The second one is the boundary conditions, and what the boundary conditions are is they pretty much tell us what happens at the endpoints of the domain of interest. And there are three types. Well, technically two, but three types. And so the first one is the Dirichlet type, and it is also known as the fixed boundary condition, and they tell us the behavior in the form that is similar to the function. So as you can see here, we have u of alpha t, where alpha is one endpoint of the domain, and this is equal to a of t. So as you can see that these are like a regular function. And the second type is a Neumann type, and this second type gives us the values of the derivative applied at the boundary of the domain. So as you can see here, we are taking the partial derivative of the function with respect to x at the point, at one of the endpoints of the domain of interest, and it is going to be equal to some function. And then lastly, it is the Robin type, and pretty much the Robin type is a linear combination of the Neumann and Dirichlet type. So that's why I kind of say it's technically two, but it's three. So yeah, and then the last thing that we need is the initial conditions, hence the initial value. And so the initial conditions, it can be one, it can be two, it can be many, but they tell us what happens in the beginning within the domain of interest. And it's usually, when it comes with like these types of problems, we're usually going to be, our second variable is going to be with respect to time. So it's usually like at time is equal to 0, what position or what temperature or whatever other variable we're looking at is at like time is equal to 0. And again, it's going to be between is going to be within the domain of interest, which our domain is between alpha and beta. And so the way that we can solve these boundary value initial value problems, or PDEs, it's, well, it is, I'll admit, it is like a pain to solve these. It is difficult to solve them, but I can say this, that even though they're much more difficult than ODEs, we can break it down to ODEs. And additionally, there are some boundary value initial value problems that are solvable and we can actually solve by hand instead of trying to do numerical analysis and getting an estimated value. And so in some cases, I can argue that the ones that we can actually solve, we can do this in 4 simple steps in order to get from the problem to an answer. And so the first step is probably one of the most crucial steps, is figuring out if the boundary the boundary condition and the PDEs are homogeneous. So in other words, if you take the equation and you set it equal to 0, does the PDE and boundary condition also equal to 0? And if it does, then congrats, you can go straight to step 4 that I'm going to show later. But if not, we're going to go ahead and go to step 2. And so step 2 is pretty much constructing a time independent solution. So that means we're going to let the function u of xt equal to u of x, and then we find the time independent solution if it exists. If it doesn't exist, that is completely okay. We can go and just do the backup and pretty much just make the boundary conditions homogeneous. There is some cases where this will not exist, and as long as we can make the boundary conditions homogeneous, we can still solve the PDE. And so the third step is to define a new function that we're going to call v of xt, which is going to be equal to u of xt minus u of x. And the reason why this works is because the functions are going to be, or are going to satisfy linearity. And so what that means is going to be something that we're going to cover later on. But because they satisfy linearity, we can use linear superposition. So that means if like two functions satisfy the PD and B and boundary conditions, that means their sum will also be a solution to the problem. But again, this is going to be like a lesson for another day about linearity and like superposition and like why these things matters and why is it that we can actually do this. And then lastly, step 4 is to solve the new homogeneous PDE and boundary condition. And so it's kind of like starting all over, but in this time it is going to be homogeneous, and from there we're going to be using the methods to solving these problems. And some of these methods include separation of variables and method of characteristics, and these are just a few methods of solving for PDEs. Others can include Bessel functions or Lagrange's equation, but in most cases it just involves breaking down the PDE into multiple solvable ODEs. And so after completing this step 4, you pretty much solve the you pretty much have solved for a general solution of the problem, and then to find a particular solution you will need to use the initial condition or conditions to solve for the like particular solution, hence the boundary value initial value problem. And so last thing like I want to cover is like why are the PDEs important. Well, this is kind of an interesting question to ask. It is the question that a lot of people ask in a lot of their classes, like why does this matter? And so for me, the reason why this matters and why it should matter to you is because they help us represent the natural phenomena that we see occurring daily. And so like notable equations that use PDEs and that are like relative to our daily lives is the actual like heat equation. So like how heat is distributed and throughout a region of space or like in a plane, and how we can actually use that to our advantage to like either be cooler or be warmer or like stuff like that. The other one is for E&M, so you physicists and perhaps electrical engineering. This is actually a mathematical representation of an electromagnetic wave, where 1 over v squared is actually 1 over c squared, where c is the speed of light, and then v is the voltage. And then you can do something similar with current, since voltage and current are related. And then lastly, we have Poisson's equation, which can be used in electrostatic, fluid flow, and Newtonian gravity. And all of these equations they're represented in 1 dimension and sometimes 2 dimensions, but we can go higher dimensions and still be able to solve them. The only difference is that you just pretty much repeat these steps over again. But yeah, that is pretty much it for this video. I'll be seeing you guys probably in the Blackboard. If not, it is going to be more likely another lecture talking about linearity and like why it matters. But yeah, other than that, I'll see you guys in the next video.